In part 2 of this section on circuit breakers, we will take a further look into the design of high voltage circuit breakers, with a particular emphasis on live tank circuit breakers. By the end of this section, you will understand all about the insulated mediums that we use inside the contact chamber, how live tank circuit breakers operate, and what additional features we need to add to extra high voltage circuit breakers. The aims of the course today are: introduce the principles behind live tank circuit breakers. Look at the features of a typical circuit breaker mechanism. Look at the additional features that we require on extra high voltage circuit breakers to deal with the voltage transients. Our aim is to obviously open the contact as quickly as possible, so that the main system can be restored back to health and we minimise damage to the circuit breaker contacts. Here's our current waveform from before. As we said previously, we have an opportunity at each current zero to break the arc. For a 50 Hz system, the current waveform crosses zero every 10 milliseconds. And for most circuit breakers, we aim to clear the fault within 30 milliseconds. High voltage circuit breakers use high capacity springs in their mechanisms so that they can react quickly and have an operating time, i.e. initiation of the trip coil to full contact opening, of less than 30 milliseconds. Let's look at the key elements of a circuit breaker mechanism. Here's a typical mechanism for a high voltage circuit breaker. First, we have the electrical closing coil for operating the CB remotely. We then have the electrical trip coil for opening the CB remotely. These close and trip coils are basically heavy-duty solenoids, which mechanically force the mechanism to operate. We have the springs to store the mechanical energy for operating the mechanism. We have the spring charging position indicator, which shows whether the springs are charged or not. We have the electrical motor for charging the springs. This can either be an AC motor or a DC motor. We have the counter for measuring the number of operations. This is important information for maintenance. We have the auxiliary switches to signal the circuit breaker position. These are connected to the same shaft that drives the circuit breaker contacts. We have the circuit breaker open or close indicator, which indicates the position of the circuit breaker. And finally, we have the insert for the manual spring charging handle. This is there in case we lose all power to the circuit breaker and need to charge the mechanism manually. These are the common insulating materials that we see inside high voltage circuit breakers. Vacuum. Vacuum contacts are used in modern medium voltage circuit breakers, as the high dielectric strength stops the arc restriking. It's used on system voltages of 6.6 kV to 36 kV. Oil. Oil was traditionally used in medium and high voltage circuit breakers. It has gradually been replaced, as the arcing broke down the oil over time, creating toxic compounds such as PCBs. It's used on system voltages of 6.6 kV to 132 kV. Compressed air. Compressed air was traditionally used in high voltage circuit breakers, with the compressed air being forced into the contact chamber to literally blow away the arc. It has been replaced by SF6, as the air compressors needed a lot of maintenance and became unreliable over time. Used on system voltages of 275 kV to 400 kV. sulfur hexafluoride gas, or SF6. SF6 is widely used on modern, medium and high voltage circuit breakers due to its high dielectric strength. It is used to quench the electrical arc inside the contacts, and when pressurized, is used as an insulating medium to reduce the physical size of equipment. Used on system voltages of 66 kV to 750 kV. On the LV system, separating the circuit breaker contacts in air is fine, as the system voltage and corresponding restriking voltage are both manageable. When we get above 6.6 kV, the restriking voltages can break down the air, and we need to replace it with a vacuum, which has a higher dielectric strength. Above 36 kV, even a vacuum is insufficient, and we need to look at the various other insulating materials that have a higher dielectric strength to insert in between the separating contacts. Let's now look at a typical live tank circuit breaker. These are very different to the dead tank circuit breakers. Firstly, we have the input terminal and the output terminal. We have the vertical bushings, which contain the circuit breaker contacts. And finally, the mechanism box, which contains all the open and closed circuits and mechanical linkages to operate the circuit breaker. We obviously don't have any space in a live tank circuit breaker for any current transformers, so they need to be purchased and positioned separately. This may increase the amount of space needed inside the substation. Let's look inside the circuit breaker bushing. At the top of the bushing, we have the fixed contact. Below, we have the moving contact, all housed inside the arcing chamber. The arcing chamber will be filled with the insulated medium, which is normally SF6 gas for most high voltage circuit breakers. At the moment, the circuit breaker is closed. Let's now open the circuit breaker. When the moving contact changes position, the pressurized SF6 gas floods into the arcing chamber, increasing the dielectric strength between the circuit breaker contacts and quenching the arc. The SF6 gas is also used as an insulating medium to separate the live conductors from the insulators. This reduces the overall dimensions of the circuit breaker. The high voltage SF6 circuit breaker is a very advanced design, and it's quite simple in its operation compared to the earlier circuit breaker types that we used to use. It relies on the fact that the dielectric strength of SF6 increases as it becomes pressurized. The shape of the gas chamber inlets are designed so that as the circuit breaker mechanism opens the contact, it also compresses the SF6 gas as it enters the circuit breaker chamber. This creates a high-pressure SF6 zone inside the chamber, which prevents the restriking voltage bridging the contacts. On extra high voltage circuits above 230 kV, one set of circuit breaker contacts may not be enough to quench the arc. In these situations, we use a double head circuit breaker. These have duplicated arcing chambers, one in each horizontal leg, both operated from the same mechanism. Let's look inside the circuit breaker to see how that works in practice. Here we have the two sets of fixed contacts and moving contacts. At the moment the circuit breaker is closed. Let's now open the circuit breaker. Sometimes, on extra high voltage circuit breakers, even having multiple circuit breaker contact chambers is not enough, and we need to add grading capacitors. These are positioned in parallel with all the circuit breaker contacts. Grading capacitors ensure uniform voltage distribution across all contact points during normal and switching system operation. They can also be used to increase the switching capacity of the circuit breaker under certain conditions. Here we have some typical examples of grading capacitors on some high voltage circuit breakers. Let's summarise what we've learned today. Live tank circuit breakers are used widely in air-insulated substations. They are unable to house any current transformers due to their compact design. Extra high voltage circuit breakers use multiple contact chambers to allow them to successfully quench the arc. Capacitors are placed in parallel with the circuit breaker contact chambers on extra high voltage circuit breakers to allow them to handle the transient voltages. Congratulations for completing this section. You should now be able to identify the key elements of a live tank circuit breaker and know all about the insulated mediums that we use inside the contact chamber. I've attached some questions on today's section to test your knowledge.